In this video, we will discuss about the stiffness matrix for truss element and stiffness matrix for beam element and the steps involved in the stiffness matrix. The first one is stiffness matrix for truss element. So consider this is the truss element having two ends, decided as 1 and 2, also called as nodes or joints. So each truss member will have two nodes and only axial forces are allowed in truss member. Therefore, we have only axial deformation, no bending. So to derive the stiffness matrix, at node 1, we have to apply unit displacement, keeping the other node, that is second node, number 2, as fixed. So due to the application of unit load at 2, unit displacement at 1, some forces will be developed at 2, node 2. And the force required to make unit displacement at node 1 also we have to account. See, now, so this is the diagram. At node 1, we have to make displacement, unit displacement. So to make unit displacement, we have to apply some compressive force at node 1. Okay? Because this is a positive direction, we are making displacement in positive direction. Therefore, we have to apply the P1 value. P1 indicates force at node 1. Okay? Along this direction. Then only we will get displacement in the positive direction. So due to this application of the P1, that is force at node 1, some reaction, just opposite and equal force, reaction will be developed in the fixed end, that is at node 2, which is equal to P2, that is force at node 2. And we know that the elongation of truss member can be expressed as delta is equal to PL divided by AE. Therefore, at 1, because we are applying P1 force, therefore delta is equal to P1 L divided by AE. Since delta is equal to 1, we get P1 value, the value required, the force required to produce unit displacement at node 1. That is P1 is equal to AE by L. And as per the stiffness coefficient definition, so this is the force due to the unit displacement. That is, this is a force at node 1 due to the unit displacement at node 1. Therefore, this is the stiffness coefficient K11. Because this first one indicates where we measure the force, the second one indicates where we apply the unit displacement. Here, both force and displacement at node 1. Therefore, K11. So, K11 is equal to AE by L. And equating sigma h is equal to 0, applying sigma h is equal to 0, equilibrium equation, we get P2 is equal to minus P1. That's just the opposite. Therefore, minus AE by L, which is nothing but K21. Because P2 is the force at node 2 due to the application of unit displacement at node 1. Therefore, K21. 2 indicates the force where we measure, and the second index 1 indicates where we apply the unit displacement. Therefore, minus AE by L indicates K21, which is also equal to K12 because of the property, symmetric property of stiffness matrix. Now, similarly, at node 2 also we have to apply unit displacement along positive direction. Okay. Therefore, so this is the diagram, and we make the other end, that is node 1, as fixed. So here this is the node 2. Now we have to make this 2 to be elongated because we apply a positive displacement. So it will be elongated to a unit amount, that is delta is equal to 1. For that we need to apply some force in the direction of that displacement. So because of this P2, we apply the P2, just some reaction will be developed in the fixed support or fixed end, that is node 1. So P2 is acting towards right side direction, therefore P1 must be acting in the left direction. Clear? Now again we have to use the expression for deflection, that is delta is equal to PL divided by AE. Here delta, we apply the load at node 2, therefore delta is equal to P2L divided by AE. And delta is equal to 1, therefore P2 is equal to AE by L, which is nothing but K22, because P2 is the force at node 2, therefore this K2, and this P2 is due to the application of unit displacement at node 2. So that's the next 2. Therefore K22 is nothing but AE by L. Okay. So P2 is the force due to the unit displacement, which is the definition for stiffness coefficient. Again applying sigma h is equal to 0, we get P1 is equal to minus P2, which is equal to minus AE by N, which is nothing but K12 is also equal to K21, which we already got in the previous step. So now we have all the stiffness coefficients, therefore we can form the stiffness matrix, or we can put all these stiffness coefficients in matrix form. So stiffness matrix K is equal to K11, K12, K21, K22, because we have only 2 nodes, 2 degrees of freedom. Only axial force is acting. Okay. Therefore, which is equal to AE by L is common term, so we can take out. Therefore, AE by L into 1 minus 1 minus 1 1. So this is the stiffness matrix for truss element. So for each single element, this will be the stiffness matrix, because each element has 2 degrees of freedom, and that is displacement at node 1 and also displacement at node 2. That's why the size of the elementary stiffness matrix is 2 by 2. Now we discuss about the stiffness matrix for a beam element or a beam member. or a simply beam. So consider a beam with the following degree of freedom, that is at each end or each node we have 2 degrees of freedom. That is at node 1 we have a vertical displacement and rotation. At node 2 we have another vertical displacement and rotation. The horizontal displacement is arrested because is neglected because it is assumed that the member is inextensible. That is, the length of the beam will not change. Okay. So here we consider only vertical displacement and the rotation. So EI is constant throughout the beam and L is the length of the beam. Now, to get the stiffness matrix for a beam, for this beam, we have to apply unit displacement or unit rotation at appropriate system coordinate, that is the degree of freedom, and the forces developed at all the coordinates, all the degree or the direction of the degree of freedom, how to be computed. Now we will apply a unit displacement at node 1. So this is a diagram for unit displacement at node 1. For this we have to do all these steps. So now to produce unit displacement at node 1, this moment 6EI, actually 6EI delta by L squared, but delta is equal to 1, therefore 6EI L squared moment is produced or applied, so that we will get delta is equal to 1. Then due to this delta is equal to 1 unit displacement, we get some reaction at that end, that is 12EI by L cube, but in general 12EI delta by L cube, but delta is equal to 1, therefore 12EI by L cube. In other words, to produce delta is equal to 1, we have to know supply 12EI by L cube reaction at that end, or force at that end. So that will develop 6EI by L square moment. So due to this, the moment, due to this displacement, unit displacement, the same moment will be in the same sense also, will be developed at the other end also. And for the equilibrium condition, the reaction also in opposite sense will be developed. So this is the scenario. So these things we have to keep in mind. So this diagram will be very useful while solving problems. Okay. So now we apply the unit displacement and we get all the forces in the appropriate direction due to this unit displacement. Now this is the time to find out the force along each degree of freedom. First we will see first degree of freedom 1. So degree of freedom 1 is nothing but the vertical direction, upward direction at node 1. So what is the force we have at node 1 in the vertical direction? Yeah, we have one force we have 12EI by L. So this 12EI by L cube is acting in the same direction as that of the degree of freedom 1. Therefore, it is a positive force. So here this direction is assumed as 1. Therefore, the force along that direction is equal to K1. And we measure this force K1 when unit displacement is applied at 1. That means K11. So this measurement represents K11 and in positive sense. Similarly, K21, that is the force at node 2 or the degree of freedom 2 due to the displacement at 1, that is K21. So 2 is nothing but rotational degree of freedom. Therefore, we have to measure moment at node 1 along degree of freedom 2. Here we have. So one moment is acting at node 1, that is which is 6 EI by L square, but the direction is just opposite. Here degree of freedom is in the clockwise direction, we assume, but actual moment is acting in the anti-clockwise direction. Therefore, this force is negative sense, in the negative sense when compared with the direction of the degree of freedom. Therefore, this is minus 6 EI by L square, and this force represents K2 and 1, because K2 is nothing but the force at degree of freedom 2, and 1, the second one, indicates where we apply the displacement, unit displacement. So therefore, K21 is nothing but minus 6 EI by L square. This K21 is also equal to K12 because of symmetric property. Similarly, the next force K31 is nothing but minus 12 EI by L cube, because this 12 EI by L cube is acting on vertically downward, but our degree of freedom 3 is vertically upward, therefore negative. Similarly, K41 is the 4-1. Here we have the moment, but acting in opposite direction, therefore minus 6 EI by L square. So these are the stiffness coefficients due to unit displacement at degree of freedom 1. Now we have to apply unit rotation at degree of freedom 2, because degree of freedom 2 is a rotational unit. Therefore, we have to apply a unit rotation at degree of 2. Then we have to measure all the forces. So this is the scenario. Because of the unit rotation, we have to apply 4 EI by L, that is 4 EI theta by L, but theta is equal to 1, therefore 4 EI by L moment we have to apply to make unit rotation. So due to this application of moment 4 EI by L, half of the moment will be carried over to the other end because of the fixed end. The other end is fixed end, therefore 2 EI by L moment is there. So in order to balance the system, balance the member, reactions are created in opposite sense. Here 6 EI by L square in the vertically downward, here 6 EI by L square vertically upward. Now we can calculate K12, K22, K32, K4 as usual. Say K12 is nothing but, here this is the 12, so minus 6 EI by L square. Then K22 is nothing but is 4 EI by L, but it is in clockwise direction, therefore positive 4 EI by L. Then this is the value for K32 plus 32, because these are in the positive direction, plus 6 EI by L square. And this thing is K4 2 is also in positive direction, therefore plus 2 EI by L. Next we will apply unit displacement at degree of freedom 3. So this is the scenario for the application of unit displacement along degree of freedom 3. For that we have to apply force total EI by LQ. Because of this application of total EI by LQ, moment is introduced at the both sides. So this is due to the equilibrium condition. At fixed support or fixed end, we have reactions in opposite sides. Now we can assign K13, K23, K33, K43. So K13 is nothing but this one, but in the opposite sense, therefore minus total EI by LQ, and this is K23 in the positive sense, therefore plus 6 EI by L squared, and this is K33 is also in positive sense, therefore K33 is nothing but 12 EI by LQ, and this is K43. This is also in positive sense, plus 6 EI by L squared. So next we have to apply unit rotation at a degree of freedom 4. So this is the scenario for the application of unit rotation at node 2. So to produce unit rotation, we have to apply 4 EI by L moment. Due to the application of 4 EI by L, half of the moment will be carried over to the fixed end, therefore 2 EI by L. So in order to keep the structure in equilibrium condition, reactions are produced. Here 6 EI by L squared in a vertically upward direction. In the fixed end, we have 6 EI by L squared in the vertically downward direction. So from this figure, we can easily get the values of K14, K24, K34 and K44. So this is nothing but minus K14, this is nothing but K24 positive, so this is nothing but K34, this is also positive because of co-direction, and this finally K44 is also in positive sense. So now we have all the parameters, stiffness coefficients. Now we can formulate a stiffness matrix for the beam. So this is the stiffness matrix for the entire beam member. EI by L cube into 12 minus 6L minus 12 minus 6L minus 6L 4L square 6L 2L like that. Okay. So next we will see the stiffness equation which we will use while solving problems. So in stiffness equation, actually the equilibrium equation, we equate the forces. So force P is equal to stiffness into the displacement. Therefore, so from this stiffness equation we can find out the force vector. No, not the force vector, actually the displacement, delta. So delta is equal to K inverse into P. Okay, but force vector P is nothing actually having two parts, PL minus PF. PL is actually the load acting directly along the degree of freedom. PF is the fixed end moment due to the span law. That we will see in detail while solving the problem. So finally, the steps involved in the stiffness matrix method are: first we have to find out, or we have to identify the degree of freedom and disseminate the system coordinates at each degree of freedom, starting from 1. Next we have to calculate the joint force, especially at degree of freedom. Once we have the joint force, then we can formulate the force vector P, which is equal to PL minus PF. The next step is to formulate the stiffness matrix by applying unit rotation or unit displacement. The next, we have to apply the stiffness equations. Once we have the delta, theta and delta, we can apply slope deflection equation to get the moment. So these were simple steps involved in stiffness matrix method. So this is the end of this lecture.